Hi everybody, I hope this video finds you well. In today's video, we're going to be working through practice number 9, which focuses on some questions related to hypothesis testing and confidence intervals for one sample mean and two sample mean procedures. As always, I recommend that you've tried this practice ahead of time, and of course that you've watched all the videos on one sample mean procedures and two sample mean procedures before watching this video working through practice 9. If you have already tried practice 9 on your own and watched those corresponding videos, well, then we can go ahead and get started. So let's look at question 1 here. So whenever we're looking at these types of questions, the first thing that we should sort of notice before we read all of the text is, of course, that down here we see that we're going to be carrying out a hypothesis test and building a confidence interval. The reason I call attention to that is because that tells us that as we read this paragraph, we want to make sure that we're thinking about which type of procedure is this going to be. Is this going to be a one sample mean? Is it going to be a two sample mean? Is it going to be matched pairs? So not only do we want to read the question for the relevant information, but we also need to be thinking about what pieces are going to tell us which procedure to use in the later parts of this question. All right, with that in mind, let's go ahead and look at this. So we're saying that we suppose that we often use a food delivery app. And we believe that the app's estimated delivery time is on average lower than the actual delivery time. Now, that right in there tells us something important. We're seeing this mention of on average. That tells us we're working with quantitative data. That should be no surprise, considering we see all quantitative pieces of information down here. But it also tells us that it is indeed going to be one of these mean procedures. Is it a one sample mean? Is it a two sample mean? Is it matched pairs? We don't know yet, but the use of that word average in there tells us it is a mean-based procedure. So, to study this, you select over the next few months every third delivery and record the estimated delivery time and the actual delivery time. And we have this note here. You may assume that you use this app a lot. In other words, there are lots of deliveries to choose from. And we get the following data. So here are the estimated delivery times, and then here is how long each of those actually took. So one of them, they estimated it would take 25 minutes. It ended up taking 43. One estimated 35, and it actually took 32. One estimated 15 actually took 17, so on and so forth. So we've got a couple things that we're supposed to do with this. So let's look at these questions and then talk about diagnosing which type of test this is going to be. We're going to talk about what type of sampling was used here. Remember, when we say what type of sampling, we mean what sampling technique. So that could be SRS, it could be stratified, it could be cluster, it could be systematic. So we need to choose which type of sampling was used here. Then in B, we're going to carry out the hypothesis test to test our claim. Remember, our claim was that we believe that the app's estimated delivery time is on average lower than the actual delivery time. And then we're going to build a 95% confidence interval for the average difference between estimated delivery and actual delivery time. All right, so at this point, it's probably a good idea to think about what situation is this going to be. Is it going to be a one sample mean? Is it going to be a two sample mean? Or is it going to be matched pairs? Well, the first thing we should see here is that we do indeed have two sets of data. So we should be thinking either two sample mean or matched pairs. Those are both ones we perform when we have two samples of quantitative data. And of course, in this situation, the two samples are matched. For each single delivery, we have its estimated delivery and we have its actual delivery. So we have the estimated and then we have the actual. So for each delivery, we have two pieces of information that causes this to be a matched pairs situation. So we're just going to make a note here. This is going to be matched pairs. So when we get to parts B and part C down here, we're going to be using the matched pairs analysis. Again, remember, a common hint for matched pairs is you see the data organized like this, which shows you how the matching worked. We can see that this one was matched with this one was matched with this, etc. So this sort of format for the data really gives you a hint that this is matched pairs. Okay, so let's go ahead and start answering the questions individually on the next page. So for part A, we wanted to get the sampling technique. So again, just as a quick reminder, sampling techniques were covered at the very beginning of our course. Remember, for our choices, we have SRS, stratified, cluster, and systematic. Technically, there was a fifth sampling technique that we discussed, which was convenience sampling. But keep in mind, convenience sampling is not valid for doing actual statistical inference. And that, of course, is what a hypothesis test and confidence interval are. They're inferential statistics. So the sampling technique of convenience sampling isn't going to be something that's possible here. So which of these is it? Well, if we look back here, we can see that the way that we built this sample is it said that you, over the next few months, you select every third delivery. Remember, whenever you select every kth individual, that is a systematic sample. So in this case, we know that this one is going to be systematic, and that's told to us via every third delivery. So we know that this was done using a systematic sample. Why is it such a big deal to think about the sampling technique ahead of time? Well, for two reasons. One is, of course, it's review that we should be comfortable with, right? We want to be still able to diagnose the appropriate sampling technique. And the second thing is, remember that systematic is very special because in the text of this paragraph, it never mentions the word random. In SRS, stratified and cluster, the word random is going to be in the paragraph, which is important because when we get to the conditions of the hypothesis test and confidence interval, one of the conditions is that the data must be random. So it's important to analyze here that since it's systematic, it counts as random even though the word random doesn't appear in the text. So this is going to be important for verifying one of the conditions later on. All right, now we're ready to move on to the hypothesis test. And remember, we're going to be doing this at alpha equals 0.05. And we've already decided that it is a matched pairs hypothesis test. And again, it is a matched pairs hypothesis test because we have two samples of quantitative data, the estimated and the actual delivery times, and we know that this is matched with this is matched with this is matched with this, so on. All right. Before we get into the specifics of this hypothesis test, remember that when you're doing matched pairs, you're not actually going to use this data set or this data set. Instead, the data set that's going to be important are what we call the differences. So we're going to calculate the differences here. Now, when you do the differences, you're doing subtraction. So you can choose if you want to do, say, the estimated minus the actual or the actual minus the estimated. Keep in mind here that if we just look at most of these, 25 versus 43, 35 versus 32, 15 versus 17, 30 versus 44, it looks like the actuals are generally higher. Not always. I mean, this one right here is a little bit lower, but most of the actual delivery times are higher. So we probably want to do actual minus estimated so that we get mostly positive values. That just makes it easier to work with. So we're going to do the actual minus the estimated. So let's get those differences. So 43 minus 25, that's going to give us 18, and then negative 3 and 2, 14, 11, 3, 3, 10, 9, 6, 8, and 8. So there we go. That is going to be our data set. So if you're following along on your calculator, this, of course, right here, these differences, this is what we want to go ahead and put into L1 so that when we actually get to the moments of needing the mean and the standard deviation, this is the data that we're going to be referencing. All right, now we can actually begin this hypothesis test. So remember, hypothesis tests are always 5-step processes. So we start with some hypotheses. So that means we need to write down the null and the alternate. Remember that since it is matched pairs, the notation here is going to be D equals some value and then D with some inequality and that same value. So we've got two things to do here. We need to figure out what value should go there, and then we need to figure out what inequality should go here. So let's go back and see if there's a baseline sort of assumption here. Well, if we're looking here, the claim, remember, is we believe that the estimated delivery time is on average lower than the actual delivery time. Notice that an amount is not given. We're just saying that we think that it's lower. So what's the baseline assumption then? Well, the baseline assumption is, if we haven't studied this yet, we would think that the estimated delivery time and the actual delivery time are the same. Well, that would mean the difference would on average be 0. So that is going to be our null hypothesis value here. We're going to be doing D equals 0. We talked a little bit back when we first introduced matched pairs that this is something that can sometimes happen with matched pairs. If you don't see a null hypothesis value given in the paragraph, that generally means that the null is going to be 0, which basically means that the null or baseline assumption is that there is no difference. All right, what about the alternate? Well, we might look back here and say it says lower, so we're supposed to do D less than 0. But we need to be careful. The way we choose the alternate in a matched pairs is based on how we calculate the differences. Notice we did the actual minus the estimated. So if the estimated is going to be lower, these differences are supposed to be positive because the estimated is supposed to be smaller, or at least we're claiming that the estimated is smaller than the actual. So that means here that it should be d greater than 0. A little hint is that oftentimes in matched pairs, if you use the trick of picking the larger set of data and then subtracting the smaller ones, trying to get mostly positive values here, then generally speaking, the alternate is going to be that greater than, because you've sort of chosen to subtract in a particular way so that you're getting those positive larger values. All right, as a note here, we should also sort of say that this is one-sided. Remember, hypothesis tests are one-sided or two-sided based on this inequality. If you use a greater than or a less than, it is one-sided. If you use a not equals to, it is two-sided. That's going to be important when we get to step 4, the p-value. All right, before we get there, though, we have to look at the conditions. So the conditions, first, the data is supposed to be random and representative. Normally, we just say that's stated, but this time we have to be a little bit careful, right? We want to make sure we remember that systematic equals random. And that's why that first condition is satisfied, the fact that we use systematic sampling. There was no mention of the word random in the paragraph, so we can't just say it was stated. Instead, we have to remember that the systematic sampling technique counts as random. All right, the second thing we have to confirm is that the sample size is less than 5% of the population size. Now remember, sample size is something we're always going to know. Population size, we may or may not know. The sample size, if we go back here, is how many of these deliveries or differences we calculated. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we know our sample size is 12. What about the population size? Well, if we go back in here, is there any mention of the overall number of deliveries, the population of deliveries? No. But there is a note that says you may assume that you use this app a lot. In other words, there are lots of deliveries to choose from. So we can go ahead and just say lots of deliveries. So for this one, we'll just make a note that we were told lots of deliveries. And there we go. That's sufficient. So again, in the situation where the population size is not given or there's no information about the population size, you simply want to say lots of and then correctly identify what that population is. All right, and finally, condition 3. Condition 3, there's two ways of checking it. Sometimes we have enough data, greater than or equal to 30 data points, that we can just say we have enough data. Unfortunately, in this case, like we said, the sample size is pretty small. It was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's not enough data to just say via the central limit theorem that the sampling distribution is going to be approximately normal. Instead, we need to actually investigate the normality by looking at a stem and leaf plot of this. Notice that these data points, if we just did a normal stem plot, we'd have like -0, we'd have 0, and we'd have 1 as a stem. That's not quite enough, so we're going to do a split stem plot here. So a split stem plot. So remember, a split stem plot, we're going to put all the stems twice. Notice that we do have to have a separate -0 and +0 stem for the negative and positive single-digit numbers up here, like these guys and those. All right. In the first 0, well, you got to be very careful with negatives, right? We're getting larger as we go this way. So this would be all the negatives that would have leaves 5 through 9. Were there any -5 through 9s? Nope, there was only a -3. So that -3 would actually go into the second -0, because again, we're getting larger as we go this way. Then this would be the positive zeros that would have leaves of 0 through 4. So let's see. Looks like we had a 2 and a couple of 3s. So 2 and 3, 3. So put that 2 and 3, 3. Then this would be the 0 for leaves 5 through 9. So let's see there. So it looks like we have 6, 8, 8, and 9. So 6, 8, 8, 9. 6, 8, 8, 9. Then this would be everything with a stem of 1 and leaves 0 through 4. So 0 through 4, looks like we'd have 0, 1, and 4. So 0, 1, 4. 1, 4. And finally, this one would be anything with a stem of 1 and leaves 5 through 9. So that would be the 18 right there. So there we go. We can do a quick check. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 data points. Okay, so we did get all of our data points. Does this look like what we want? Well, this does look like there is no strong skew, right? If we sort of look at this, looks like it does have sort of that nice tall part in the middle and balanced on both sides, so there's no strong skew. And most importantly, there are no outliers. There's no negative, like, negative 35 or something way down there, or something like positive 52 or something. So there's nothing way out there. So all the data is pretty clumped together. So we're good with those conditions. So all three conditions necessary to do the matched pairs hypothesis test have been met. So we can now go ahead and move to the test statistic. For the test statistic, we need our formula. It is going to be a t-test statistic because we're working with quantitative data. We're going to be taking the average of the sample differences minus the null hypothesis over the standard deviation of the sample differences divided by square root of n. So there are sort of four things we need to know here. We need to know the average of the differences, the null hypothesis, the standard deviation of the differences, and the sample size. So some of these things we have, remember the null hypothesis right here, d equals 0, so we've got that. And of course the n, we've mentioned it several times, we have 12 data points here. How do we get this d bar and st? Well, that of course is going to be from putting this data into L1. So let's go ahead and do that. If you're following along in your calculator, go ahead and put in those differences. So 18, negative 3, 2, 14, 11, 3, 3, 10, 9, 6, 8, 8. And then we do stat calc 1 var stats, just like we used to do all that. And when we get that, we look at x bar. Of course, our calculator doesn't know that these are differences, so it reports it as x bar, but we know that they're differences. So we'll put that as d bar, 7.4. And the standard deviation, we want the sample one, looks like 5.7 there. So let's go ahead and plug that stuff in. So up top, we have 7.4 minus 0 over 5.7 divided by the square root of 12. Always go ahead and do the top and bottom separately. So up top we have 7.4 because 7.4 minus 0. And in the denominator we have 5.7 divided by the square root of 12. Looks like we should end up with 1.65. Then we'll go ahead and do that division. 7.4 divided by 1.65. Looks like we should come out with a t-value, our test statistic of 4.48. Okay, so that's the main computational step. Now we're ready to go ahead and get the p-value. So we'll be getting our p-value. Remember, to get the p-value, we need to look this up on table C. Why do we use table C? Well, that's the table that tells us about t-test statistics. To go on to table C, we need to know the degrees of freedom. Degrees of freedom is n minus 1. So in this case, that's 12 minus 1, which is 11. So we're looking for this test statistic, 4.48, with 11 degrees of freedom. So let's go ahead and take a quick look at table C to do that. And we'll pick a sort of color to do that in. So we're looking this up in blue here. So 11 degrees of freedom. So we've got table C right here. There's our 11 degrees of freedom. And 4.48 puts us right over here. T equals 4.48. Notice that 4.48 is past the largest t-value for degrees of freedom 11, which would be 4.437. So we can now follow that down, and we'll follow this all the way down to the one-sided p. So this would be our p-value right there. Why are we using one-sided? Well, keep in mind that that goes back to our alternate, which we said d greater than 0. We have a one direction. We thought that the differences would be greater than 0, so it was one-sided. So if we look there, our p-value should be located there. These p-values get smaller as they go this way, so our p-value needs to be smaller than the smallest one. So we can report here that according to all that, our p-value comes in less than the smallest one, which was less than 0.0005. So as a percentage, we know that the p-value is less than 0.05%. So the p-value is incredibly small here. Remember, in general, large t-values correspond to small p-values. They have an inverse relationship there. All right, we are now ready to write our conclusion. So let's take our conclusion here. To make our conclusion, we compare this p-value against the alpha of 0.05. Remember, 0.05 is set in the problem. It says that back up here. So how does the p-value compare? Well, the p-value, we don't know exactly what it is, but it is smaller than 0.05%. This is 5%, so our p-value is way under the alpha. When the p-value is under the alpha, remember the statistical conclusion we make is reject HO. So whenever the p-value is smaller than alpha, we reject HO. What does that mean in context? Well, rejecting HO is successfully rejecting the null, meaning we successfully found evidence for our claim. So we'd say significant evidence, that, and then what was our claim? Well, we could say that the differences on average are greater than 0, or we could go back to the original way that we phrased the claim, that the estimated delivery time is lower than the actual delivery time on average. So, significant evidence that on average, the estimated delivery time is less than the actual delivery time. Super important, though, that you get that phrase on average in there. It does not mean that every delivery has an estimated delivery time less than the actual one. Remember, there was one where the estimated delivery time was actually 3 minutes longer than the actual one. So we're not saying this uniformly. We're just saying that on average, this seems to be the case, right? That's what this conclusion is saying. So super important to have that phrase on average in there. Okay, so we've now detected that there is evidence that the average estimated delivery time is less than the actual delivery time. Let's go ahead and follow it up with the last part of this, which is to estimate how big of a difference there actually is, right? Which is building the 95% confidence interval. So we'll go ahead and give ourselves one more page. So now we want to do a 95% CI for the average difference. When you see this phrasing of average difference, that means you're going to be using some sort of two-sample procedure, either a two-sample mean confidence interval or a matched pairs. Of course, we already know that it's a matched pairs because that's how we did the hypothesis test. So this is going to be a matched pairs confidence interval. So confidence intervals are two-step processes. So we've got to check some conditions. Of course, one of the benefits of doing a confidence interval after a hypothesis test is the conditions, at least for the procedures we've discussed so far, are the same. So we can just simply say already checked. So we don't have to do any additional work there. Now, what if question B wasn't part of the assignment? Well, then we'd have to check the conditions just like we did here. They would be exactly the same as these. We'd have to actually check them at this moment. But of course, in this case, we already did the hypothesis test, so we don't have to worry about checking the conditions here. For step 2, we have our construction. This is our formula, so it's going to be d bar plus or minus t star sd over root n. So we need to know 4 things here: d bar, sd, n, and t star. Now, because this is a confidence interval, there is no null hypothesis, right? Hypotheses don't make any sense when we're talking about confidence intervals. So these first 3 things are all about the sample, the data. So we can just carry these over from what we had here. It'll be that 7.4, that 5.7, and that 12. So let's write those in. 7.4, 5.7, and 12. T star, how do we find that? Well, we need to go ahead and use table C for that. So once again, in this one, we're going to be intersecting degrees of freedom, which were 11 here. And we're going to be intersecting that with the confidence level, which was specified as 95%. So we'll do that in blue as well. So let's go take a look. So there's 95%. And if we intersect those two together, notice we get that value there, 2.201. So that is going to be our T star here. So our T star, 2.201. All right, now we can plug everything in. 7.4 plus or minus 2.201, standard deviation 5.7 divided by square root of 12. Now we actually want to sort of determine what this interval looks like. Let's go ahead and handle the margin of error here first. So 2.201 times 5.7 divided by square root of 12. You can just type that all in one line in your calculator. And you should get 7.4 plus or minus 3.6. If we go ahead and then we calculate that, 7.4 minus 3.6. Remember, you always want to do the subtraction first to get the low end of your interval. 3.8, and then 7.4 plus 3.6, we should get 11.0. Then we need to write a quick interpretation. Anytime you interpret a confidence interval, always start with the level of confidence. So we'd say 95% confident that on average, well, okay, again, we have to have that phrasing of on average because that's what we're doing our inferential statistics about here, the average. Well, that this is where the average, remember we were estimating average difference, so 95% confidence that on average, the difference in estimated delivery time and actual delivery time is between 3.8 and 11.0 minutes. So we now have an estimate for how big that difference is on average between what they estimate and what actually happens. On average, we're saying it's somewhere between 3.8 and 11.0 minutes. Does that mean that almost all the deliveries are 3.8 to 11.0 minutes later than anticipated? No, not at all, right? Because this has nothing to do with individual deliveries. Remember, this is a confidence interval about the average. So that's why it's so important to have this specified here. This does not apply to individual deliveries. Remember, if we look back, some of the deliveries certainly fell in this range, right? You know, these guys all in here fell in that range, but this one was 14 minutes later, 18 minutes later, those were outside this range. This one was 2 minutes later, that's outside the range. This one was 3 minutes earlier, that's outside the range. This range has nothing to do about individual or single deliveries. It's all about the average overall in terms of all the deliveries, their estimated time versus their actual delivery time. Okay, so this first question, the main thing to keep in mind here was that when you see data like this, you should be immediately thinking matched pairs analysis, and that's how we did both the hypothesis test and the confidence interval. All right, let's go ahead and move on to question 2. So for question 2, once again, notice that there's mention of hypothesis test and confidence interval in here. So we know that as we read this, we want to be thinking not only about what is the sort of relevant information, but what type of procedure, one sample mean, two sample mean, or match pairs are we going to do here? So let's go ahead and go through this. So we're going to suppose that a small university, around 15,000 students. Why is this in here? Well, whenever you see something like that, you know that that's giving you the population size. Again, a lot of times we don't know the population size, but this is going to be one of those instances where we actually do. We can see that they conducted a campus-wide study in 2010 that asked their current students to grade their satisfaction with the school on a scale of 1 to 10. So they found that the average satisfaction rating was 82.5. So that was in 2010. Now in 2017, the university wants to know if the satisfaction rating has changed. To study this, the university randomly selects 15 classes from the course schedule and samples all the students in those classes. They ultimately end up sampling 400 students. So we know that this right here, those 400 students, that's going to be our sample size. They ask each of these students to grade their satisfaction with the university on a scale of 1 to 100. They get an average score of 84 with a standard deviation of 16. So this average score of 84, that's going to be our X bar. How do I know that that's our X bar? Well, because that's the average of the sample. Yeah, so that's our X bar. And the standard deviation of 16, that's going to be our S there. Okay, you notice the only thing that we didn't sort of identify yet is what is this 82.5 going to be? It's certainly going to be important, but we'll have to think about what that actually is going to be. So let's go ahead and get started with this. We'll talk about the sampling first. So what type of sampling was this? So again, that's SRS, stratified, cluster, or systematic. Well, we can rule out systematic right away. There's no mention of taking like every 10th student or every 20th student. Instead, really all the information about how they did this study is right here. They randomly selected 15 classes, but sampled 400 students. So they picked classes, but then once they picked a class, they took all the students in those classes. So remember, whenever your number of selections doesn't match the actual sample size, right? We only made 15 selections, but we ended up with 400 students. That means that every time we picked one of those classes, we added a bunch of people to our sample. Well, that basically meant that we added clusters to our sample. So this one would be a cluster sample. And we selected these 15 classes. Each class was a cluster, and when we did that, we added a bunch of students to our sample. So this would be a cluster sample here. All right, now let's get to B and actually start thinking about what procedure this is going to be. So is this going to be a one sample mean, two sample mean, or matched pairs? Well, we can see here, if we look at our data, of course, we're talking about means because we have these words like average and standard deviation. So that tells us we have quantitative information. And how many samples do we have? Well, we only end up sampling 400 students. We have one sample here. So this is going to be a one sample mean hypothesis test. That means that this one sample has to be compared against a known or assumed average. And that is exactly what that 82.5 is going to be, because that's what happened back in 2010. We would think that unless there's evidence to the contrary, things haven't changed since 2010. So this will be our baseline assumption. So this is a one sample mean hypothesis test. So let's go ahead and start with the hypotheses then. We'll also just make a note again that the alpha is 0.05. Of course, that's just right there. So what do the hypotheses look like? Well, it's always a null and an alternate. Because we're doing one sample mean, the format is going to be mu equals a value, and then mu some inequality, and that same value. So once again, we have two things to sort of determine here. What value is going to go in those two spots, and then what inequality? Well, what should this null hypothesis be? Remember, it can't be the average of 84 because that's our data. So there's only one other average specified. That was the average back from 2010, the baseline assumption. So that 82.5, that is your null hypothesis. So we know that this value should be 82.5. In other words, if nothing has changed, we would still say the average satisfaction rating is 82.5. And what inequality should we use? Well, we want to look for our claim here. If we look here, we see we want to study if we look back, right, we want to know now in 2017, the university wants to know if this satisfaction rating has changed. So changed indicates we don't think it's necessarily gone up or down. We just want to know if it's changed. That means we're going to be using not equals to. Remember, changed is one of those key words for not equals to as your alternate. That is going to make this test a two-sided one. Why is it two-sided? Because we're using that not equals to there. All right, let's go ahead then and look at the conditions. So first condition needs to be random and representative. Well, it does say right here that they randomly selected 15 classes, so we have that stated. So we're all good with that. 2, we need to check that the sample size is less than 5% of the population size. We know the sample size, that we are always going to know that. In this case, it's 400. And we made mention that we do know the population size, 15,000. So we can directly check. We need to see n equals 400. Is that really less than 0.05 times 15,000? Well, we can just check on our calculator. 0.05, remember 0.05 for 5% there, times the 15,000 equals 750. Is that a true statement? 400 less than 750? Yep, we're all good there. Finally, for condition 3, in the last question, for condition 3, we had to do a stem and leaf plot. Is that necessary here? Well, not only is it not necessary, it's impossible because we don't have the raw data. Instead, we just have to simply note that we have a lot of data, n equals 400. That is certainly greater than or equal to 30, so we're all good there. Remember, really what's going on behind the scenes here is that since we have 30 or more data points, the central limit theorem assures us that regardless of what the population's shape is, the sampling distribution, which is what we're using, is going to be approximately normal, so we can proceed. All right, let's go ahead and get our test statistic then. So we'll do that over here. Our test statistic is t equals x bar minus mu over s over root n. We want to make sure you have each of the formulas for each of the 3 procedures we've discussed so far. What do we need to know here? We need to know x bar, mu, s, and n. Well, we've already talked about the mu. It's right there, 82.5. That's the null hypothesis. We just discussed the sample size, 400, so we'll need that there. And now we need to somehow find the x bar and the s. In the previous example, we did that by using the one-var stats feature because we had the raw data. Here, that's completely unnecessary because we know that the average and the standard deviation for the 400 students came to 84 and 16 respectively. So we'll just pop those in, 84 and 16. All right, let's go ahead then and plug all that stuff in. 84 minus 82.5 over 16 divided by the square root of 400. Always go ahead and do the top and bottom separately. So 84 minus 82.5 means we get 1.5 up top, and then 16 divided by the square root of 400 means that we get 0.8 down there. And then we'll go ahead and actually do the division. 1.5 divided by 0.8 looks like we should get 1.88 as our t value. All right, so let's go ahead then and look that up. So now we're ready to go get the p-value. So we need to use table C here. And what should the degrees of freedom be? Well, it's going to be 400 minus 1, which is 399. Now, if we just take a quick look ahead, table C has lots of degrees of freedom, but it does not have 399. It starts to skip down here. Remember, if your degrees of freedom is not listed, you always just round down. So 399 is going to be rounded down to 100. So we're just going to make a note here. We're going to use degrees of freedom equal to 100. So we'll go ahead and we'll do that in green here. So we're looking for this 1.88 with degrees of freedom being 100. So let's go and see. So there's 100 degrees of freedom. 1.88 looks like it's going to put us, if we're following along here, 1.88 is bigger than this one, but smaller than this. So we'd find ourselves right here, 1.88. And then we'll drop down to the two-sided p. Why are we going to the two-sided p? Because again, we are using the not equals to here, which makes this a two-sided test. So we find ourselves here with our p-value ending up right there. So remember, the p-values get smaller this way. So the low end of our estimate is 0.05. The high end is 0.10. We know our p-value lands somewhere between 0.05 and 0.10. So let's go ahead and record that. So our p-value is somewhere between 0.05 less than the p-value less than 0.10. So we know that the p-value needs to be greater than 5%, but we also know that it's less than 10%. So it's somewhere sandwiched between those two values. All right, let's go ahead and make our conclusion then. So last step, if we take this p-value and we compare it against the alpha of 0.05, well, we know that our p-value is somewhere between 5 and 10%, so it is certainly bigger than 5%. So our p-value here is greater than alpha. What does that mean the statistical conclusion is? Well, that means we're going to fail to reject HO. So remember, failure to reject HO is the same as failure to find evidence. So we would say no significant evidence for our claim. What was our claim? Well, that the average has changed from 82.5. So no significant evidence that the average satisfaction rating has changed. Now you could say has changed since 2010 or from the score of 82.5, whatever you prefer. So I'll say has changed since 2010. So once again, we have that phrase, the average, because we're not talking about individual satisfaction ratings. We're talking about average satisfaction ratings. And we're saying that there's no evidence that that average rating has changed since 2010. Alrighty, so there we go. We've gone ahead and done part B, which was a one sample mean hypothesis test. Finally, let's go ahead and wrap this up with part C, which is we're going to build a confidence interval for this. So for part C here, we'd like to build 95% CI for average satisfaction rating in 2017. So we know we're going to be using our data since that was collected in 2017. So notice that this is a 95% confidence interval for the average rating. So not an average difference, which might mean it's a two sample mean or a matched pair. It's just an average of something. So this is going to be a one sample mean confidence interval. Perfect. So the conditions, well, we've already checked those, so we don't need to do anything there. So already checked. And then the construction. So for the construction, we have our formula, x bar plus or minus t star s over root n. We need to know four things there, x bar, s, n, and t star. all the sample stuff we can just carry over. So the x bar was 84, sample standard deviation 16, and n was 400. So we've got 84, 16, and 400. This t star, we need to look that up. So to remember to do that, we're going to take on table C, the degrees of freedom is 399, and we're going to use 100. We're going to intersect that with the confidence level, which is 95%, and put those two together. And again, the confidence level comes directly just from the statement of the problem. So 95% and 100 degrees of freedom. So we'll zoom out just a little bit so we can see that. Okay, so there's our 100. We'll go across down this guy here as well. Put those together. Looks like we're right there. So they would intersect, and our t star is going to be 1.984. So if we go back here, our t star, 1.984. Perfect. All right, let's plug that stuff in then and actually figure out what this interval looks like. So 84 plus or minus 1.984, 16 over the square root of 400. Let's go ahead and get this margin of error first. So 1.984 times 16 divided by the square root of 400. And we should get 84 plus or minus, looks like we get 1.59. And if we go ahead and do that, subtract first, 84 minus 1.59, we get 82.41, and then the high end, 84 plus 1.59, it looks like it's 85.59. So we would say we are 95% confident that the average satisfaction rating is between 82.41 and 85.59. Now again, does this mean that 95% of students ranked it as between 82.41 and 85.59? Not at all, right? This has nothing to do with individual ratings. Instead, we're saying that this is the interval we're confident on for the average of all the satisfaction ratings if we talk to every student on the campus. Notice that this does match up with our conclusion in part B, which was the hypothesis test. Notice this range says from about 82.41 up to 85.59 is believable. Notice the old null hypothesis, 82.5, is in this range, right? 82.5 is in this range. So 82.5, which was the value back from 2010, is still believable. That's why we failed to reject it. Okay, well, let's go ahead and turn to the last question on this practice. So for question 3, once again, same sort of setup. We've got the hypothesis test and the confidence interval. So as we read this, we want to make sure we're not only just thinking about what are going to be the important pieces of information, but also what type of procedure are we going to be using here. So let's go ahead and see what we have here. We want to study if female Facebook users have more friends on Facebook on average than male Facebook users. So to do this, you first divide the country into 4 regions. West Coast, East Coast, Midwest, and South. Then you randomly sample men and women from all 4 regions and pool them together to make your 2 samples. That right there tells us a key piece of information. We have 2 samples, right? So we should just keep in mind that. That probably means we're using one of the 2 sample procedures, either match pairs or 2 sample means. Ultimately, you end up sampling 120 female Facebook users. So that is going to be a sample size, 120 female Facebook users, and 150 male Facebook users. You find that the female Facebook users have an average of 166 friends with a standard deviation of 58. 166 and 58. Those are going to be important values. And the male users have an average of 141 with a standard deviation of 66. So there we go. Let's first, before we start talking about the procedure, let's just figure out the type of sampling. So again, type of sampling could be SRS, stratified, cluster, systematic. Again, systematic, we saw what that looked like in the first question. It says like every 5th, every 10th, every 15th. That doesn't mention here, so we know it's not going to be systematic. Was there anything special with how we did this? Well, we did, right? First, we divided the country into 4 regions: West Coast, East Coast, Midwest, and South. And then we sampled some people from all 4 regions. So we did some initial classification. We divided the country. So if you divide up initially, or you do some initial classification and take some people from each one, that makes this a stratified sample. So this is a classic example of a stratified sample. The strata, the groups, are the regions, the West Coast, East Coast, Midwest, and South. We wanted to make sure we got some people from each one. Okay, now let's go to B. We're going to do the hypothesis test. What type of hypothesis test is this going to be? Well, like we said, we know it's two samples. Are they matched together? No, they're two totally separate populations. We have female Facebook users and male Facebook users. So this is going to be a two-sample mean hypothesis test. Remember, in general, two-sample mean is used when you have two samples from two separate populations. And that's exactly what we have here. Female Facebook users, male Facebook users. And of course, the alpha, 0.05. All right, let's get started on that then. Let's talk about the hypotheses. So the HO and HA, what is the format for this? Well, remember for the null, for two-sample mean, it is always preset. It is always that mu1 equals mu2. Now, in this case, we can use some subscripts. We know that our first population is female Facebook users. So we'll say mu sub f equals mu sub m. The average number of friends for female Facebook users is the same as the average for male. That's what our null or baseline assumption is. What's the alternate? Well, we can look back at our claim. We want to study if female Facebook users have more friends on average. So we're saying that we would expect the average for females to be greater than the average for males. So there's our alternate. So that was the only thing we had to determine because remember, for two-sample mean, this is always just going to be equal. What type of test is this? One-sided or two-sided? Well, since we used greater than, this is going to be a one-sided, right? Since we have that greater than there, it is one-sided. All right, let's go ahead and check the conditions. Remember that when you have a two-sample procedure, you have to check the conditions for each sample. So the first one, they both need to be random and representative. Of course, it was stratified and randomness was stated in there, so that's stated. Both samples need to be less than 5% of the population size. Now, we have some sample size information. We know that we talked to 120 female Facebook users and 150 male Facebook users, but notice there's no mention of how many overall female and male users there are for Facebook. So all we can do here is just assume that there's lots of those. So we'll say lots of female Facebook users. That seems like an okay assumption. And lots of male Facebook users. That also seems like a fair assumption. And finally, for condition 3, we need to either look at a stem and leaf plot, which is not going to be doable since we don't have the raw data, or we have to have large enough sample sizes. And we do. N1, well, remember, 1 is now going to specify our first population, which is females. That was 120, so sample size 1 was 120, which is certainly greater than or equal to 30, so we're all good there. And N2, which is now going to specify our second population, males here, that was 150 users, so that is also enough, 150 greater than 30. So we're good. Both samples were large enough that the central limit theorem is going to assure us of normality. All right, we're now ready to move to the test statistic. So for the test statistic, we have T equals x1 bar minus x2 bar over the square root s1 squared over n1 plus s2 squared over n2. So this is one of the more complicated test statistic formulas, but let's just go ahead and remember this, and this all reference the first sample, which is going to be females. This, and this all represent the second sample, which is going to be males here. So we need 6 things before we can plug in. Okay. So we need to know the average standard deviation and sample size for females first. So what was the average for females? Well, we can look back up here. It was 166. The standard deviation for females was 58. And the sample size for females, well, we just did that. It was 120. For males, the average was 141. For males, the standard deviation was 66. And the sample size was 150. So let's plug all that stuff in there. So up top, we're going to have 166 minus 141, and then divided by big square root 58 squared over 120 plus 66 squared over 150. Now again, a couple little details. If you do type this in piece by piece, that square only applies to the standard deviation. So you're doing 58 squared and then dividing by 120, 66 squared, and then dividing by 150. You can actually type in the top and bottom separately in one line each. So let's go ahead and do that. For the top, if you take 166 minus 141, should get 25 up top. And in the denominator, if we type that in, square root first, then 58 squared divided by 120 plus 66 squared divided by 150 should get about 7.55 in the denominator. Then we'll go ahead and do the division. 25 divided by 7.55. And it looks like we should get 3.31 for our test statistic. Perfect. Now we're ready to go ahead and get our p-value. So we'll do it in purple this time. So to do that, we need to go on to table C, and we need to get our degrees of freedom. Now, degrees of freedom, usually n minus 1. We have to be careful here. We have two different n's. So which one are we going to use? Well, we always use the smaller one. So the degrees of freedom here is going to be 120 minus 1, which is 119. Now, 119 isn't going to show up on there, so we're going to end up having to use 100, which is the smaller. Remember, we always round down. So we're looking for 3.31 with a degrees of freedom of 100. So let's go ahead and do that. So we've got 100 degrees of freedom here, and we're looking for what did we say? 3.31. So if we do that, 3.31... looks like we should be right here, 3.31. So that puts us between 3.174 and 3.390. And if we follow that down, we'll be right there. So our p-value is bigger than 0.0005, but smaller than 0.001. So there we go. So our p-value here, we just figured out, is bigger than 0.005, but is smaller than 0.001. Perfect. Now we're ready to make our conclusion. So our conclusion here, our p-value, how does it compare against the alpha of 0.05? Well, we know that the p-value is somewhere between 0.05% and 0.1%. This is 5%, so the p-value is certainly smaller than the alpha. That means the statistical conclusion is that we are rejecting HO. So we've had a successful rejection here, so that means we have significant evidence for our claim. What was this claim here? Well, we were saying that on average, female Facebook users have more friends than male Facebook users. So significant evidence that on average, female Facebook users have more friends than male Facebook users. Again, so important to put on average. This does not mean that every female Facebook user has more friends than every male Facebook user. It's just saying on average, female Facebook users have more friends than male Facebook users. All right, so that was a two-sample mean hypothesis test. It's not probably one of the most complicated and sort of messy test statistics, but again, the actual 5-step procedure just runs like every one of the other hypothesis tests. All right, let's go ahead then and build an estimate for how big that difference actually is, now that in part B, we actually diagnosed there was a difference. So we'll give ourselves one more sheet here. So we want to do a 95% confidence interval for the average difference in friends between female and male Facebook users. So notice that we're doing a confidence interval for the average difference. So we want to use one of our two-sample procedures, either two-sample mean or match pairs. It is not match pairs here. So this is going to be a two-sample mean confidence interval. Now, as a note, what if it said 95% confidence interval for the average number of friends for female Facebook users? That would be a one sample because it would just be about females. If it said a 95% confidence interval for the average number of friends for male Facebook users, that would be a one sample mean confidence interval because it would just be about males. It's the fact that it says the average difference between these two groups and the fact that we know that the two samples were not matched together that makes this a two sample mean. So we go to the conditions. Because we've done the hypothesis test, we know that those have already been checked. And then we can go to the construction. So the formula for the two-sample mean confidence interval is x1 bar, sample average, minus x2 bar. That's our point estimate. Then plus or minus t star, and then that messy s1 squared over n1 plus s2 squared over n2. So if we've got all that, we're then ready to just figure out what all those values actually are. So there's 7 things we need here. We need x1 bar, s1, n1. We need x2 bar, s2, n2. And we need t star. Now, it is good to stay consistent here. So since we have females first and males second, that's also how we did the hypothesis test. We want to also do that here. So all of this should represent the female sample. So the average was 166, standard deviation 58, and sample size 120. So we got 166, 58, and 120. Here, all this should represent the male sample. So the average was 141, standard deviation 66, sample size 150. So 141, 60, and 150. Or 66, excuse me. So let's go back and just touch that up. 66. Okay. And then we need to get the t star. Now that we do need to look up on the table. So this is going to be table C. Our degrees of freedom, still going to pick the smaller one, 120, subtract 1, so 119. And then, of course, we know we're going to use 100. And the confidence level is 95% again. So we're going to intersect those two together. So let's go ahead and do that. So we've got 95% again, and we've got 100 degrees of freedom. Oh, we're actually going to have the same one we had in the previous one, 1.984. So 1.984. Alrighty, so we have our t star, just like the previous one. All right, let's plug all this stuff in. So we have 166 minus 141 plus or minus 1.984 square root 58 squared over n1, which is 120, plus 66 squared over 150. All right, most of the time we just go ahead and go straight to the margin of error, but this time we also have to handle the point estimate. So let's go ahead and do that subtraction. 166 minus 141. That's 25 plus or minus. Now we can type this part in. 1.984 times, then the square root, 58 squared divided by 120 plus 66 squared divided by 150. So if we go ahead and type all that in, we should get a margin of error of 14.99. If we go ahead and then do the subtraction, 25 minus 14.99, looks like the low end should be 10.01, and the high end, 25 plus 14.99, looks like we should get 39.99. So let's give our interpretation of this. We're 95% confident that on average, well, we could say the difference between the number of friends that female Facebook users and male Facebook users have is between these two values. Or if you want a slightly fancier way, keep in mind what we did is we took the average for females and subtracted the average for males. And this is all positive values. So this tells us that this is how much more, or on average, how many more friends female Facebook users have than males. So we can say 95% confident that on average, female Facebook users have between 10.01 and 39.99 more friends than male Facebook users. Again, notice that we said 95% confident that on average, got to say that. And this is, again, not a statement about individuals, but it's a statement on average, how many more friends these female Facebook users have than male. So there we go. This did our example of a two-sample mean confidence interval. So in this practice, again, you got to see each of the major hypothesis tests we've discussed so far, one sample mean, two sample mean, and match pairs, as well as their corresponding confidence intervals, and did a quick review about sampling techniques.